So here are the three topics that we're gonna discuss today. First, we'll discuss about longitudinal shear. Even though we apply shearing force in vertical direction, we could have the longitudinal direction shear. If we have this kind of cross section. So we're gonna discuss about why there is longitudinal shear stress and how we can obtain the stress. After talking about the longitudinal shear, we'll talk about shearing stress in thin-walled member. I mean, the member with thickness is much smaller than height and the thickness B. And as a last topic of shearing stress, we'll discuss about unsymmetric loading case. So let's start from the longitudinal shear case. So the question that I want to open this discussion with is this. So is the equation Q equals to be delta H over delta X, which is the same as VQ over I, is true for any arbitrary section? Yeah, the answer is following. So let's consider a cross section. So instead of having some beautiful and symmetric section, out of this cross section, let's take this red area. So here we have area 1 and 2 and 3. Yeah, these three side wall for this red cross section. What you can see here is the tau at surface at top, which is 1, is 0, and tau, which is the shear stress at surface 2, is 0. Okay, and if we consider the force equilibrium, in the direction coming out of this plane or paper, what you can see here is you can also do same thing. Like the integral range is this area where you have compressive or tensile loading due to the moment, and for the right hand side surface you have same thing, and you have this delta H3 which acts on the entire this curved surface. You can think about this curved surface and delta H, okay, as a like a side wall at three sides. And what you have to think is under the mechanical equilibrium, this equality must be hold. Okay, and you can contract first and second term, which gonna result in this equation, and you have delta H3. And if you define Q3 as delta H3 over delta X, if you take this little tiny section with thickness delta X, then you can see that by dividing this by delta X and delta X, this becomes V, and you have I, and you have this integral Q. So if you take this integral range of this Q as this curved and interesting shape red area, then you can apply the same thing. So the answer is yes for the first question. Now we can think about an different geometry and application of the equation. So suppose that you have a beam made out of like four plates, and these four plates are connected by nails. This wood plates, you have like this nails located periodically, and they are connecting this and 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 this. Okay, so somebody can ask like what should be the like a minimum maximum distance between this nail to sustain the shear force V given the strength of the nail. Then you can answer the question using the equation we just discussed. Okay, so here what you can realize is following. So suppose that out of this front end cross section, let's take this as the red area. So if you think about the area 1 and area 2, this is open and free surface, so tau must be 0, so you don't need to worry about force acting on 1 and 2. Now if you draw this in different view angle, what you can realize is tau gx and tau xy must be equal to each other. So what you can realize is if you take very small section out of this, if you take section with delta x, and let's try to do same thing. So you have a left hand side and right hand side such that you have this contracted effect of moment in left hand side and right hand side, and you have force from this third sidewall and fourth sidewall, delta H3 and delta H4. So if you define Q3 and Q4 as delta H3 over delta X and delta H4 over delta X, then it could be defined as this. And if you move this entire thing to the right hand side, and if you also divide this by delta X, you can see that this becomes V, and you don't have a minus sign after moving to right hand side. You keep this I, you have our famous Q integral. Now the integral range is limited to here. Okay, so and what you can see here is because of the symmetry between 3 and 4 surface, third and fourth surface, what you can see here is it must be same as 2 times Q3. Okay, so you can see that Q3 must be V over 2I, and Q, and the integral range is this red one. Okay, so by doing so, you can obtain shear stress acting on exactly this and this surface. And because shear stress here and shear stress here, they are equal to each other, then you can define and think about the force acting on this nail. Okay, so that's how you can handle this problem. Okay, not only this section, what you can do is, as a function of this distance from the center L, you can obtain the Q. Okay, so how can we do that? So if you take this red area as the symmetric area, you can see that in top and bottom, you have like a zero shear stress. For left hand, this side and that side, you have exactly same Q. So what you can realize is, let's try to obtain Q red area. So Q red area must be same as area of this red one, and the you have to consider the centroid position of this red area. So centroid position is halfway through this guy from the centroid. Okay, so you can obtain Q integral as 2 times L times D multiplied by y bar. Okay, so this is 2L, the height is D, and you have y bar. And if you consider tau xy or tau gx, which is shear stress acting on here or acting on the sidewall, if you consider delta H over delta X and delta D, so if you draw this in different angle, you have D here, you have delta X, you have delta H. Okay, and this one is same as Q3 over D. Q3 is defined here, and Q3 is defined as V over 2I Q red block. And if you plug in the expression for this Q red one, and here you end up having tau xg tau zx is equals to be VL over I y bar, and y bar is the centroid position of this guy. Okay, so what you can see here is, as you have like a located, as you consider a position located further and further from the center position, this shear stress is getting larger, and that's why you're gonna see some shearing stress diagram, something like this. Okay, so now with this, by considering the applicability of this equation for arbitrary sections, you can think about why there should be and how can we obtain the longitudinal stress for the vertical shearing force. Okay, so with that, let me finalize the first topic here.